Welcome everyone to this talk on the quantification of inhaled soot mass using Pathfinder coupled results. Now, we don't only quantify the inhaled soot mass, but we also quantify the inhaled CO mass. And you may ask, why, Brecht Debrouwere, why do you at CERN want to know the inhaled soot mass and the inhaled CO mass? Well, for that, I'll give you a little bit of context. So first, FIRIA. We are doing this in the FIRIA project. I'll explain very shortly what FIRIA is and what it stands for. Then we'll look at how the assessment of an effective radiological dose is done currently. Then finally, we will talk on the methodology, which is methodology update for FIRIA. And finally, we will look at an example how we applied this new methodology. So what is FIRIA? FIRIA stands for Fire-Induced Radiological Integrated Assessment, and it is basically a methodology to look at what the effects would be of the combustion of a radioactive fuel in one of our experimental areas. So where experiments happen at CERN, we may have irradiated materials, which then in turn become radioactive fuels. So this is an example of TCC2, where we have radioactive fuels. So would a fire in one of those lead to potentially radioactive smoke, which potentially could affect firefighters and potentially escape, and in turn then potentially affect bystanders and potentially people outside of the CERN fenced area. So the FIRIA project looks at all of this and is, as it looks like, a very interdisciplinary project. So this is a joint effort of the HSE unit. So together with fire engineers, RP physicists and environmental protection specialists and the fire brigade, together with the IT department and the ENCV CFD team, so that's our CFD team, we are working all together to find an answer to these questions. And because it's so interdisciplinary, our chair of the project steering board is Benoit Delille, who is leading the HSE unit. The project manager for this project, this large project, is Saverio Lamendola, and the deputy PM is Oriol, Rios. So this is a project which was started in 2018, and it's still ongoing, and we are going through multiple iterations, and it is really a success story so far. So very shortly, what we do is we first look at how radioactive those fuels would be, and we do that through calculations with a computer software which is called FLUCA. With that, we calculate the RP radionuclide inventory. RP stands for radio protection. Then, using that information, we use FDS to do fire modeling and smoke transport modeling, and then we look at how the smoke would spread and how it could escape to outside of the facility. Using that information, we use Pathfinder to run evacuation calculations, to look at the toxicity of smoke and if occupants can get out safely, and this is also where this new methodology will be used. And we look at environmental dispersion. So environmental dispersion is when the smoke leaves, what effect would it have on bystanders and on people outside of CERN fenced area. So here you can see in red picture where the smoke is moving, and for that we use ANSYS Fluent. Now, all of this information from all of these simulations is used by the fire brigade to develop their fire intervention tactical plan, to find out how to tackle fires in the safest way possible, and is also used for a radiological environmental impact assessment. So one of those assessments that looks at effective doses, so effective radiological doses, it looks at the pathways through which a reference person outside the CERN fenced area is affected by the smoke plume. This model assumes a reference person standing still, and then, as you can see, there are multiple pathways through which people can be exposed. So either through external exposure to the plume, through inhalation of those particles in the plume, and then those particles can be deposited either to dry deposition or wet deposition, the difference being the rain, and then through ingestion of vegetables, of milk, or of meat, the person can be exposed again to those radionuclides. And then finally, through resuspension of dirt on the ground and inhaling that, people can be exposed again to those radionuclides, or finally external exposure immediately to the ground. Now, This is true for people outside of CERN's fenced area, and this is partly true for bystanders. Bystanders may not ingest meat grown in the area or may not ingest milk from the area, but for occupants, that is not the case. So occupants would not ingest any vegetables or meat or milk from the area, is one of the assumptions. Now, so only one or two of those pathways are then critical for occupants. That's direct exposure to the fuels and radioactive environments, which is then also true in the normal case, and for which we have a very good understanding and very well developed radio protection models. And the second pathway, which is the pathway we are investigating now, is the pathway of inhalation of smoke. So this presentation will look further into how we quantify this. Now, first of all, we have already a few models to look at what inhaled soot has for effects. So first, there's the toxic gases and toxicity of the smoke, and those effects, they are integrated already in Pathfinder. So the effect of inhaled toxic gases and visibility on occupants is something which we already can do with Pathfinder and with the tools which are at hand today. RP, so our colleagues from radio protection, they already have models to look at the effect of radioactive gases and soot particles on still standing bystanders and the effect of direct radiation on occupants. So that's the first part of the pathways that I was telling you about on the slide before. But finally, we need then a model for the RP effect of the inhaled radioactive gases and soot particles of occupants evacuating. So not occupants standing still, otherwise we could use the same model as for bystanders, but if you use that on occupants, well, of course, the biggest dose you would receive by inhaling smoke from straight above the fire, which is not realistic, which is much too conservative. So we would ideally like to have a model where we can use, such as Pathfinder, moving agents, and using that output data to look at the inhaled amount of soot and inhaled amount of CO, then to scale. So this methodology would look something like this. First of all, we calculate the time-dependent concentration of soot and CO in every point with FDS. Then we import that data in Pathfinder, which then outputs the encountered concentration. And after running the evacuation simulations, we can then calculate the inhaled amount of soot or CO. Now, we can assess the amount of radionuclides which are inhaled if we know that soot is coming from fuel which is radioactive, and that way we know how much becquerel is inhaled. And finally, our colleagues at RP can convert this activity in becquerel to a committed dose in sievert. So this new model is based on existing calculation tools. For evacuation, we use Pathfinder, and Pathfinder gives us an output on visibility and the CO volume fraction, and we can convert that to the amount of soot present per time step and the amount of CO present per time step, mass amount. So the conversion then to how radioactive the soot would be and what radionuclides would be present in the soot is done by assuming that all of the radioactivity in the fuel is converted to radioactivity in the soot by this formula, in which YS is the soot yield, AS is the specific activity in the soot, and A fuel is the specific activity becquerel per kilogram, in the fuel. So this is then used for particles deposited on soot in liquid or solid state, but not all particles, not all radionuclides are in the liquid or solid state. Some of them are in gases, so iodine gas, for example, but then that can be scaled with CO. So the same formula is valid, except for YS soot, we use YCO. So then, how do we convert the visibility into the soot mass fraction? So that we do with these two formulas. So first of all, we see the correlation between the visibility and the soot mass fraction in yellow. And in the second correlation, we see how the smoke density is correlated with the temperature and with the smoke or air density at ambient temperature. So everything in the dotted line is variables that we know. Everything in the green line is output, or in the green circles rather, is output that we get from Pathfinder, and the yellow ones is the ones that we are looking for. So we know how to calculate that. Then for the mass fraction of CO, we use a similar approach, and with these formulas we can quickly see that we just need the molar mass of soot, of smoke, and the molar mass of smoke is about the same as the molar mass of air, and we use the molar mass for CO. So that way we can convert the volume fraction for CO, which we get as an output, to mass fraction of CO. So finally, last step, we use Purser's model, and then with Purser's model, we can calculate the inhalation of the mass of soot. So scaling with soot happens with the first formula. Scaling with CO uses the second formula. They're very much alike, except that we use the YCO instead of the YS, and the mass fraction of CO instead of the mass fraction of soot. So, as an example, this is a picture of the TCC2, which I explained before. So that's an underground facility, and you can see immediately that there is a lot of cable trays here, which contain irradiated cables. So that's a potential fuel with radionuclides in. And here is the beam. So around the beam we have magnets. Those magnets contain resin. That resin is at ambient temperature and gets heated up when the beam is active. That can start burning. Shortcuts, there are always reasons why this magnet resin could start burning. So that magnet resin also contains radionuclides. So we developed some scenarios, and then we've, as I already stated before, did FDS calculations on those, and then Pathfinder calculations. So the smoke plume here is one of the results of the FDS calculation, and you see here an agent. Now that agent is a result of the Pathfinder calculation, and what was particular about this scenario is that the agent actually evacuates through the smoke, so this way, towards the nearest exit, because the software had programmed it that way. Now, this exit was much closer than the other exit, which was much farther away. And we have seen in literature that people indeed sometimes evacuate through smoke, but that they would rather choose the way away from smoke. So this is a very conservative calculation, very conservative approach, but we cannot exclude it. So this is something that we kept in the results. Now then, these are the results, and you can see that for the person evacuating through the smoke, who has inhaled a lot of smoke, even there we only are at 14% of the maximum reference dose. So we can say that the results are acceptable. And you see for the other scenarios, we have percentages of up to 3%. So yes, these are acceptable results. Now then, looking at the conclusions, this novel methodology allows us to quantify the effective dose due to inhalation with moving agents. This methodology is then also highly scalable to other properties. So we don't only have to look at radioactivity, we can also look at gases, liquids, or solids. So for example, imagine lead content in fuel, asbestos content. If we assume that all of those, and we don't even have to assume that, we can change the methodology accordingly, but if we assume that those travel in soot, then we can also quantify those for occupants and for other people around. A disadvantage of this new methodology is that post-processing is still time-consuming, so it would be beneficial to add this functionality as a built-in property in FDS and Pathfinder. However, we also realize that this requires more flexibility on the definition of plot 3D properties and more flexibility on the interlinking of them. At this point, only 5 properties can be defined in FDS. It would be beneficial if more can be defined, and the interlinking of them, so Pathfinder only allows for the 5 predefined ones. It could be nice to have more and more flexibility on them. So thank you for your attention. Are there any questions?
Okay, can you hear me well now?
Yeah.
Okay.
Yes, now I can hear you. Hi.
Hey, look at that. You'll see my face too. I'm sorry. Oh, I've got like a highlight. Oh, look at that. Stained glass and a glow.
It's a halo. Yeah.
Dearly beloved, let's see. So we do have a couple of questions. Thanks for joining us. The first one's from an online participant. Says, thank you for your interesting topic. Please let us know what height is the inhaled soot taken from for the life safety criteria, and also consideration of inhalation after occupants travel down exit staircases would be considerably higher than on the same level exit. I'm assuming from some increased respiratory function potentially. Do you have any comments on those 2 points?
Yeah, so on the first comment, what height? So we took 1.8 meter, but that's free to choose to whatever height you want to get your FDS calculation. So you could also, or not the FDS calculation, but the Pathfinder calculation. So you could adjust that to 2 meter, but we chose 1.8. Now on the second topic, so it's true that if you have some exercising, then the inhaled amount of air, so mass of air would be higher. So that would affect your calculation. So in the formulas that I've included in the paper as well, so that's RMV mass. So the mass of inhaled air. That would be higher. So for the calculations that we used average exercise. So what is typically used when evacuating. So we didn't take specific values into account for someone who would be doing hard work, but the methodology allows for it to do so, yes.
Okay, and I may not have caught it, our audio was a little low. What was the head height? Were you using the 90% height from Pathfinder?
Yeah.
Okay.
Yeah, we did, but and that way we so reverse engineered it to 1.8 meters height as the inhaled height where you would inhale. But that is quite high compared to the average height of people. So it is rather conservative, but it's adjustable as you want, of course.
Okay, great, thank you. And then Kevin, I think you had a question.
In regards to the POT 3D output, is it possible to use the 3D slice feature? So we have a function in FDS by which instead of just having a two-dimensional slice of data, you can have a three-dimensional output. So for a given scale or quantity, you could save all of that quantity in all of the grid cells. Would that work?
So, sorry.
Yeah, I was going to say we have currently Pathfinder only uses plot 3D data that it samples from and uses that volumetric data.
Okay.
But it is restricted to the 5 quantities that it's limited to. So there is a feature request, a suggestion to allow for slices, 3D slices, and then maybe you could bound that of like some height or down stairwells. Come up with some method of making sure you capture all of the volume that would be respirated.
Okay.
And then use that data for the occupants to do the FED calculations.
Okay.
Yeah.
So is that your job or my job?
I know one of the things we had talked about in the past was maybe a more compressed, like a more compressed 3D volumetric data set.
Okay.
So that was something we had talked about, kind of like I think you do like temperature and some other things in like the S3D formats now.
Yes.
And being able to do any quantity in that format.
Okay.
Potentially. So that was something in the past that had been talked about, but Slice 3D would work, and you could do like a lower, a dump rate or lower frequency.
You can also have these so-called smoke 3D outputs, as many as you want.
In any quantity?
Yeah.
Okay.
Yeah, and I'll talk to you more about
so
that later.
That might be the way forward with that too.
Yeah.
So,
okay.
Yeah, and that would then expand Pathfinder's capability to sample any quantity. The other was like radiative field, if we were trying to have some sampling of radiative flux, and that was the other, like how to do that through a 3D volume and have people experience some amount of flux.
Okay,
so,
all right.
Anyway, yeah. Did I answer for you there?
I couldn't have said it any better way. So,
yeah, it's a work in progress, that's for sure. Any other questions here in the room? And I don't see any online. Okay, well with that, thank you very much for joining and for participating. Appreciate it.
Thank you, it was my honor.
Have a good evening.
Yeah, thanks for joining us, Greg.